Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 25, Design of Binary Magnitude Comparators. This lecture is the part of Chapter 5, Arithmetic Network Design, for the course titled Digital Logic Design, or Digital Electronics, or Digital Systems. The next slide is a disclaimer for you to read. I cite 3 references in digital logic design, but there are many others online. Chapter 5 contents, we talked about design of binary adders, we talked about design of binary subtractors. Today we'll talk about design of binary magnitude comparators. Then we'll talk about design of binary multipliers, design of ALUs, which is arithmetic and logic units. Then we'll end up the chapter with the HDL design 4. M-bit comparator. An M-bit magnitude comparator is a combinational system with 2 M-bit numbers representing positive integers A and B and 3 outputs F1, F2, and F3, indicating the relationship between the magnitudes of the numbers A and B, such as F1 will be equal to 1 if and only if A is greater than B. F2 will be equal to 1 if and only if A equals to B. And F3 will be equal to 1 if and only if A is less than B. Magnitude comparators find many applications in digital systems and microprocessors architecture. Actually, we will talk about magnitude comparators in the microprocessors course. There are many instructions based on the comparison between 2 magnitudes such as A and B. Now also I should mention that F1, F2, F3, there will be only one function will be equals to 1 at a time. So we cannot get really F1, F2, and F3, all of them 1, or 2 of them are 1. Only one function has to be equal to 1, and the other 2 functions must be equal to 0. Now, the block diagram of n-bit magnitude comparator is as shown. We have n-bit number A and n-bit number B. We are comparing those 2 numbers, and we have 3 outputs, F1 if A is greater than B, F2 will be equal to 1 if A is equal to B, and F3 will be equal to 1 if A less than B. Now, let's design 1-bit magnitude comparator. A 1-bit magnitude comparator is shown in the block diagram and in the truth table, and with 3 functions, F1, F2, F3, and 2 inputs, A and B. Each input is 1 bit. So the block diagram is very clear. The truth table, when we compare actually A and B, 0 to be compared with 0, they are definitely equal. So F2 will be equal to 1, while F1 and F3 are equal to 0. A and B, if A is 0 and B is 1, so definitely here is A less than B. They are not equal. A is not greater than B, so it will be 0. It is not equal, will be 0, but it is less than B, so it will be 1. If A is 1 and B is 0, A will be greater than B, so F1 will be 1. They are not equal, so it is 0, and will be A is not less than B, so F3 will be 0. When we have 1, 1, they are equal again, so you find F2 is 1, while F1 and F3 are 0. So from the truth table, we can find F1, F2, and F3 as a sum of minterms. So clearly F1 will be A, B prime, A, B prime. F2 will be minterm 0 plus minterm 3, which is A prime, B prime, or AB, and F3 will be A prime B, Fe prime B. So we know that F2A prime B prime or AB will be equal to exclusive NOR. Okay, so you can see here it is exclusive or the output inverted. You can get F3 in the hardware circuitry, in the hardware implementation, the one-bit comparator. And this is direct implementation. We have an AND gate, which is the input is A, and we have B prime to give me F1, and we have here B and A prime inverted complemented A to give me F to an AND gate to give me F3. So simple design, we can replace this design with all NAND gates. We know this structure, the 4 NAND gates would give me exclusive OR. If we invert it, if we invert the output, we'll get F2. And if we take the output from here, which is AB prime all prime, complemented, so if we take it to an AND gate, will give me F1. And the same thing here, if we take it to an AND gate, to an inverter, will give me F3. AND gate with the same, with 2 identical inputs is equal to an inverter. So this will give me a 1-bit magnitude comparator. If we'd like to design a 4-bit magnitude comparator, we can do with the truth table method, or simply we can use a logical approach if we want to. So if we consider a 4-bit magnitude comparator, the input A will be A3, A2, A1, A0, and B will be B3, B2, B1, B0. The two numbers are equal if A3 is equal to B3, A2 is equals to B2, and A1 is equals to B1, and A0 equals to B0. The equality relation, so F2I in general, F2, it is AI prime, BI prime, or AI BI, or AI BI. This came from this equation, really. F2 is equal A prime, B prime, or AB. Now, when we have multiple inputs, multiple digits in A and multiple digits, so F2I will be AI prime, BI prime, or AIBI, or AIBI. So it is generalization to this equation. Generalization to this equation. I do believe here there is a typo here. So it is AIBI, where F2I will be equal to 1 if the paired bits AI and BI in position I are equal. That is, both are 1s or both are 0s. If A is equals to B, F2 will be 1, and this can be achieved only when all F2i's are equal to 1. This will yield an AND operation of all F2i's as follows. So we say F2 will be F23 and F22 and F21 and F20. So because for the equality sign, so logically, without going to the truth table, we proved to have F2 equals to 1, we need F23 equals to 1, F22 equals to 1, F21 equals to 1, and F20 has to be equal to 1. Okay, so simply we can do that. To determine if A greater than B or A less than B, we inspect the relative magnitudes of pairs of digits starting from the most significant position. If the digits are equal at the most significant position, we compare the next lowest significant pair of bits until a pair of unequal digits are reached at position I. So if AI then greater than BI, then A will be greater than B. Alternatively, if AI is less than BI, then A is less than B. So we need only one digit at any position it's greater or less than the B digit at the same position to make determination. So how logically we can prove this? We say the following. F1 is equals to 1 if A3 is greater than B3. This is the most significant bit. See, this is came again from this equation. F1 is equals to AB prime. F1 3 at the third position will be A3 B prime 3. So when we get equality, when we get larger than, the same thing with the less than, F3 is A prime B. So for less than, the most significant bits, A has to be 0 and B to be 1. So what we say here, we say that logically speaking, F1 is equals to 1 if A3 greater than B3. So if A3 is 1 and B3 is 0, you will get A3, which is 1, and 1, which is 1, will get F1, 1. But if A3 and B3 are equal, this term will be equals to 0. So we check the next two digits. We need A2, B2 prime. So if they are equal, it means F23. F23. This is because F2 is the equality sign. F23, you remember F2? It's F23, F22, F21, F220. So if the most significant bits, if they are equal, it means F23 is 1. So logically speaking, we can say the next term of this of 1 will be F23. If F23, then A2 has to be greater than B2, or F23, A2, B2 prime. But if both bits, the most significant bit and the next bit, are equal, it means F23 and F22, A1, B1 prime. And the next term will be if the first three bit, the most significant positions are equal, it means F23, F22, and F21 are all ones, so we need A0 to be greater than B0. All this will satisfy F1, so logically we derived F1 without going to any truth table. The same thing with F3. F3 is less than. So for A less than B, we need either A3 prime B3 is equals to 1, or A3 less than B3. So if A3 is 0, get A3 prime 1, and B3 will be also 1. So at that time, this term will be 1, and F3 will be 1. But if those are equal, it means F23 will be 1. So the next two digits we test them is A2 prime B2. And the next two digits we test is F23 and F22, we need A1 to be less than B1. So it will be F23, F22, A1 prime B1. And the last test, which is the least significant bit, we need A0 to be less than B0. And F23, F22, F21, it means the most significant three bits in the two numbers, they are equal. And by doing this, logically we derived F1 and F2, and also logically we derived F2, which is F23 and F22 and F21 and F23. It's really super easy. It's very simple. It looks complicated, but it is not. So logically we derived three equations for 4-bit magnitude comparator, and we can do the same for any n-bit comparator, magnitude comparator. Now the question is how we design this. A 4-bit binary comparator, we know that 4 NAND gates, okay, with inverter here will give me the equality sign for the digits A3 and B3. So we have the inputs here. I hope you can see them. I have A3, B3, A2, B2, A1, B1, and A0, B0. So we start with the most significant bit. So we verify that F23 is 1. We need to test the output of the second set of the 5 NAND gates. Okay, this has to be 1. If this is 1, we feed it back here. And this has to be 1. We feed it back to the last sequence, the output has to be F2 will be 1 here with the test of the least two significant bit, which is A0, B0. So this is the sequence. We prove that F23 is 1, F22 is 1, F21 is 1, and F20 is 1. And by ending all these, we'll get F2. So this circuit fully verified. See, the feedback will be the last. So those 3 NAND gates will become a 3-input NAND gate. The feedback that we take it here to those set of 3-input NAND gates. Here, there's a short circuit here. The same thing, we took the output. The circuit fully verified and tested and fully implemented in hardware and also tested and fully correct circuit. Also, we take the 4 outputs from here to get F1, which is for the number A to be greater than B, we need the function F1 to be 1. So we take the output from this NAND gate and from this NAND gate and from this NAND gate and from this NAND gate. All of them, they go to the 4-input NAND gate to get F1. And for F3, which is A less than B, we get the outputs from this NAND gate and from this NAND gate, from this NAND gate, and from this NAND gate, and this definitely will give me F3, okay, in this 4-input NAND gate. Now this circuit, as I said, fully verified, you can test it, and it is very fast comparator. There is a feedback in it, so it is very fast comparator, and you can get the answer really fast to compare 2 numbers, 2 4-bit numbers, A and B. Now, we can design a 16-bit. If we know how to design a 4-bit comparator, we can design a 16-bit comparator. And this is a modular one by using the chip 74LS85, which is a 4-bit magnitude comparator. We can expand it to 16 by using 4 modules or 4 chips. Or we can expand it to 20 if we want to, or higher order. Okay, now this chip, the inputs to the chip has a CN, a carry N for less than, for equality, and for greater than, equality, and less than. So the input has to be 0, 1, 0. This is how the chip's designed as initial carry N for the first chip. The output, which is greater, equal, and less, will be taken to the next chip, and so on and so forth, as many chips as you want until we have the last one. So the first chip will handle the least significant bit, which is A0 to 3, B0 to 3. Those are the inputs. So then we have the next significant bits, which is 4 to 7, then 8 to 11, then 12, 15. So A will have a 16-bit number, and B will have a 16-bit number as well. A 16-bit number, and this will be a 16-bit iterative magnitude comparator by using the 74LS85. This will be the end of this lecture, binary magnitude comparator. I would like to thank you so much. Please subscribe by clicking on the circle logo with the letter I in it, and hopefully to see you very soon. Sincerely, Dr. Hassan.